Assalamualaikum everyone. My name is Kiran Amin and I'm from BS Physics department. Today I'm going to give the assignment of quantum numbers. The set of numbers used to describe the position and energy of the electron in an atom are called the quantum numbers. Let's look back to its history. The quantum number was the first number discovered and it was done so by Niels Bohr in 1913. Bohr thought that each electron was in its own unique energy level, which he called a stationary state, and that each electron would have a unique value of n. Types of quantum number. Four quantum number can describe an electron in an atom completely. The principal quantum numbers, the azimuthal quantum numbers, the magnetic quantum numbers, and the spin quantum numbers. Names and symbol. The principal quantum numbers are represented by n and maybe 1. Its value may be 1, 2 or 3. The azimuthal quantum numbers is the angular momentum. L for n is equal to 3 and L may be 0, 1, 2, S, P, D depending upon the subshell. The magnetic quantum number is the projection of the angular momentum, and the spin quantum number ms for an electron, S is equal to 12, so ms is equal to minus 12 plus 12. To completely describe an electron in an atom, four quantum numbers are needed: the energy, the angular momentum, the magnetic momentum, and the spin. Principal quantum number. In quantum mechanics, the principal quantum number is one of four quantum number assigned to each electron in an atom to describe that electron state. Its values are natural numbers, making it a discrete variable. For example, the principal quantum number, the value of n ranges from 1 to the shell containing the outermost electron of that atom. For example, in cesium, the outermost valence electron is in the shell with energy level. So, electron in the cesium can have an n value from 1 to 6. The principal quantum number n describes the energy of an electron and the most probable distance of the electron from the nucleus. In other words, it refers to the size of the orbital and the energy level an electron is placed in. The number of subshells, or I, describe the shape of the orbital. Shapes. The S subshell can hold a maximum of 2 electrons as there is only one orbital. So F orbitals are spherical in shape and increase in size as the energy level or shell increases. For example, the figure is showing the S subshell can hold a maximum of 2 electrons as there is only one orbital. So here is the only one orbital. Let's see the d orbital. The d orbital is a clover shape, as you can see in the figure, because the electron is pushed out 4 times during the rotation. As the electron push 4 times during the rotation. When it's rotating, the electron push 4 times during the rotation. When an opposite spin proton aligns, glows with the 3 spin aligned protons. And the p orbital. A p orbital has the appropriate shape of a pair of lobes on opposite sides of the nucleus. You can see in the figure, or a somewhat dumbbell shape. An electron in a p orbital has equal probability of being in either half. The shapes of the other orbitals are more complicated. And for f orbitals, the f orbitals has 15 protons to complete a fifth level of a tetrahedral structure. The f orbital is more complex but follows the same rule based on the proton alignment as the p and d orbital. As we have told before, when completely full, it is similar to the d orbital but cut in half, 8 lobes instead of 4. It is cut into 8 lobes instead of 4. The azimuthal quantum number. The azimuthal quantum number is a quantum number for an atomic orbital that determine its orbital angular momentum and describe the shape of the orbital. It is also known as the orbital angular momentum quantum number, orbital quantum number, or second quantum number, and is symbolized as L. The azimuthal or orbital angular momentum quantum number describe the shape of a given orbital. For example, if n is 3, the azimuthal number can take on the following values. It may be it may be minus 0, 1 and 0 and 1 and 2. When L is equal to 0, the resulting subshell in an S subshell, the azimuthal number, also known as orbital quantum number, determine the subshell to which an electron belongs. As a matter of result, the number of electron jump increases and the number of line at the same time for a given value of n. It can have any integral value ranges from 0 to n, as you can see in the figure. The magnetic quantum number. The magnetic quantum number is one of 4 quantum number in atomic physics. The set is principal quantum number, azimuthal quantum number, and spin quantum number. Together they describe the unique quantum state of an electron. For example, the angular momentum and the angular quantum number L can be integer between 0 and n and minus 1. If n is 3, for example, L can be either 0, 1 or 2. The magnetic quantum number M can be any integer between minus L and plus 1 L. If L is equal to 2 centimeter, can either be minus 2, minus 1, 0 plus 1 or 2 plus 2. In atomic physics, the spin quantum number is a quantum number that describes the intrinsic angular momentum of a given particle. The spin quantum number is designated by the letter S and the fourth of a set of quantum number which completely describe the quantum state of an electron. For example, we can see in this figure shapes of magnetic quantum numbers. In atomic physics, the spin quantum number is a quantum number that describes the intrinsic, as we have told above. For example, the spin quantum number tells us the orientation of an electron. The spin quantum number tells how the orientation of electron with an orbital and has 2 possible values. Ms is equal to 1 plus 1 to 1 by 2 for spin up, and ms is equal to minus 1 by 2 for spin down. If all the electrons are paired in an atom, there is no net spin because the spins cancel each others out. A quantum number is a value that is used when describing the energy levels available to atom and molecules. An electron in an atom or ion has 4 quantum number to describe its state and yield solution to the wave equation for the hydrogen atom. Shapes of spin quantum number. Here are the shapes of the spin quantum number. Thank you so much.